Thank you so much, Professor Mohanty, for accepting our invitation.
The webinar series.
With this, I will introduce Professor Mohanty. Professor Kishore Mohanty is the WA Moncrief Centennial Chair Professor in Petroleum Engineering at the University of Texas at Austin. He worked at Arco Oil and Gas Company from 1981 to 1991 and taught at the University of Houston from 1991 to 2008. His research is directed at the enhanced oil recovery, formation evaluation, improved fracturing, and nanotechnology application for oil and gas industry. He won the Pioneer Awards during the SPIOR Symposium 2008, the very prestigious Lucas Gold Medal from AIME SPE in 2013, and SP Distinguished Achievement Award for Petroleum Faculty in 2016. He has served as the executive editor on the SP Journal Board, member of the JPT Special Series Editorial Review Board, and the chair of the SP Reprint Series Committee. Currently, he is serving as a member of the SP R&D Committee worldwide. Professor Mohanty earned his BS degree from the Indian Institute of Technology, Kanpur in Chemical Engineering, and PhD from University of Minnesota, again in Chemical Engineering. And he is one of the well-known professor in the field of petroleum engineering, and it will be our great privilege to listen to his talk. Today he will discuss his work on the chemical techniques to increase oil recovery from the shales. So I invite with this Professor Mohanty to please grace the occasion and provide your insightful information on the subject matter. Thank you so much.
Thank you, Jitendra. It's a pleasure to be here and speaking to you, and especially the students who have stayed there late Friday. So let's get started. I want to first thank my students who actually did the work. Okay, I just get to present this. So I have had some very good students in the past and really enjoyed them. And we have a good group of about 12 people who work on this research. So we are working on several projects. And as you can see by the names, they're all related to improved oil recovery or enhanced oil recovery, or EOR, as we say it. But today, I'm going to speak on these enhanced oil recovery in oil shales. Okay. All right, so let's first get into the background a little bit. So here I'm showing US oil production in the last 80 years. Okay, this is 1940, this is more or less now. Okay. As you can see, in the first 30 years, the oil recovery went up. Okay, and that's because at that time they were finding new reservoirs, conventional oil and gas reservoirs. So that's why the oil recovery went up. But then they stopped finding a lot of new reservoirs. And if you don't find new reservoirs, the pressure is going down in the reservoirs, so the oil recovery goes down. That's very natural, and it falls about 5% a year or so. So the oil recovery started coming down. Okay. And it had reached a maximum of about 10 million barrels per day for the US. It came down to about half of that, about 5 million barrels per day. Then some magic happened. As you can see, the oil recovery went up. And this magic is these shales, or shale oil. Okay. And that's what we'll be talking about today. It has gone up to about 12 million barrels per day. About 60% of the oil that US produces, which is very vital to US economy, comes from these shales. That's the good news. That a lot of oil are being produced from these shales. But the bad news is that in each well, the production rate declines very fast. This is how the oil recovery comes down with time. This is in months. In the first year, about 75% of your production is gone. And it declines further. So the oil recovery, economically in the next 4 years is of the order of 5 to 8%, less than 10% in these wells. So we are leaving behind more than 90% of the oil. Okay, so why is that? So let's look into that a little bit. By the way, if you have any questions, please interrupt me and ask me as I speak. We don't have to wait till the end. Okay, let's have a discussion. So what are shales? Shales are these fine-grained sedimentary rocks. Okay, so it's almost like you take mud and you put it underground at high temperature, high pressure, it makes these shales. And they have a lot of clay, a lot of quartz, and also often a lot of carbonates. The organic contents in these things are small, of the order of 2 to 5%. But there are some shales though which have up to 30%, but most of them are like 2 to 5%. The porosity in these rocks are very small, of the order of 2 to 5%. Whereas the porosity in a normal reservoir rock, such as sandstones or limestones, that's of the order of 10 to 25%. So this is much smaller than that. The pores here are of the order of, this is a mistake, it's not micrometer, it should be nanometers. So of the order of 10 to 200 nanometers, whereas in a common reservoir rock, it's of the order of 10 micrometers. It's a much smaller. So because of that, the permeability, this is the conductivity with which fluids can flow through these porous rocks, that's very, very extremely small, of the order of 10 to the minus 6 Darcy. Whereas a typical rock is like 0.1 to 1 Darcy. This is like 10 to the minus 6, less than 10 to the minus 6 Darcy, or we call it less than micro Darcy. It's in hundreds of nano Darcy. So because the permeability is so low, things don't flow very easily. Okay. And this is the source rock, meaning this is where the oil got cooked and oil was created. And then this got squeezed and the oil moved out of these rocks into the reservoir rocks where you have conventional reservoirs. But these source rocks also have some oil in it, some hydrocarbon in it, which is actually a vast amount if you look at it. So everywhere you have a reservoir, normal reservoir that you find, there got to be a source rock somewhere around it. Okay. So in US, there are a lot of these source rocks as well as normal oil reservoirs. And this picture sort of shows that there are huge deposits of it. And these oils typically, these shales typically have some light oil or some gas, natural gas in it, typically, that you can extract out. And they are at pretty high depths, like 3,000 to 4,000 meters. So since they're so tight, you have to create a lot of surface area to extract things out of there. So what people do, they drill horizontal wells. So they drill wells that are almost like a mile long. And within that, they put in a lot of fractures, like 30 to 50 fractures. So every 100 meters or so, there is a fracture. Okay. And each fracture is like a few hundred feet long and is as thick as that formation, which is of the order of 20 to 100 feet or so. So you create a lot of surface area through this. And then what you do is very simple, just you depressurize that reservoir. So the pressure inside the reservoirs are high, and in the wellbore, you are lowering the pressure. So things expand and come out. That's how you produce these reservoirs, or that's how people are producing these reservoirs. So, so the question is, why is this recovery pretty low? In a normal reservoir, when you do this sort of thing, if you have a oil reservoir, you'll typically get about 20% of the oil out this way. if you have a natural gas reservoir, you'll get 50–60% of the actual natural gas you have in the reservoir come out this way. But these things are extremely tight, right? Very low permeability. So these things don't flow very well. So the pressure dissipates very fast into these formations. So your pressure pulses don't go very far. They go very slowly. So that's why your recoveries are so low. And there is limited reservoir energy. That's a certain, you find the reservoir at a certain pressure. As you depressurize, the pressure falls, so your production will go down. But also, the way we create the fractures are not the best way. So let me show that. So there is a picture. So this is your horizontal well, and you have created this fracture. This is, of course, in some kind of lab setting. This is not the real thing. But when you try to inject and to keep this, so what they do to create fracture, they just inject water. And if your pressure inside is higher than the pressure of the overburden, so it will create a crack there. That's what we call a fracture, hydraulic fracture. And to keep this fracture open, we inject some sand with either with water, which is called slick water fracturing, or with some polymeric water, which can carry the sand a little better. But the gravity acts and the sand is denser than the water. So sand falls. So you get a lot of sand near the wellbore. But as you go far away from the wellbore, there is not much sand. Sand doesn't make it that far. So only part of this fracture gets propped by sand. So when the pressure decreases, the two sides of the fractures close, only this part will produce things. This part almost goes back to no fracture because the two sides are, so two sides, so there is, since there is no sand to keep the fracture open, fracture closes over here. Not only that, in real systems, there are a lot of natural fractures, which are sort of perpendicular to these and connect to these fractures. And these natural microfractures are very, very small. And a lot of the sand is bigger than those microfractures, so they never get inside those. So you create a lot of surface area, but you don't keep that open, okay? So as the pressure decreases, a lot of these microfractures and part of the main hydraulic fracture closes. So that's why you are not producing anything from those areas. All right. Besides that, also as the oil and gas come out, there's some organic deposits that get left behind. Some asphaltene, wax type of things could come out and close some of these fractures, for some of these openings. That's why also the production of these natural, the fluids go down. Also, in some cases, the water that you are using for fracturing, that could seep into these pores and block the pores so that the oil can't flow out. So that also sometimes causes problems. So what can we do to improve these things? So people are working a lot of different techniques. One of them is very mechanical. So try to go put more fractures there. Of course, that's not a simple problem, because when you create fractures, you change the stress fields. And because the stress field are changed, you can't put a fracture where you just want to. You have to design it properly. Anyway, there are other faculty in our department that are working on it. We work on more chemical thermal things, sort of like the gas huff-n-puff. That's what I'm going to be talking about. So you can inject some gases. The gases can go inside the oil and re-energize it. So when you produce back, you can get some oil out. You can put some chemical blend, some water, some wettability alteration agents, and some other agents along with this gas, and also try to improve that. You can think about how to keep these microfractures open by doing something chemical. You can try to go and heat these things by heating it, you are giving some energy, and you can also improve oil recovery. So we have worked on some of these aspects. And today I'm going to talk about three things. I'll talk about gas huff-n-puff, CO2 or hydrocarbon gases. I'll talk a little bit about gas and some chemical huff-n-puff. Then I'll talk about acid micro-encapsulation to improve the properties of or conductivity of these microfractures. All right, any questions so far?
Yeah, I don't think there are any yet. The audience are actually attendees who don't have their microphones on, so they'll post their questions in the Q&A, and we will hand them over to you. Yeah.
All right, sure. All right, so let's start with the first topic. So in these formations are very, very tight, as I said, right? The permeability or conductivity is less than 1 microdarcy. So it's very difficult to inject something from one well and produce it in another well and let it pass through, hundreds of meters of the rock. That's just, it will take a very long time, meaning millions of years. It can't just flow that fast. All right. So what we can do is inject something in the same well and produce back. That sort of process is called huff-n-puff. Okay? So huff is when you are pressurizing, trying to put something into the formation, and then you lower the pressure, that's the puff, and things come out. Okay? And this kind of thing has been carried out in conventional rocks, and this picture is from that, but we are taking the same idea and trying to apply it to unconventional rocks. So in the conventional rocks, it's vertical wells, but in these unconventional rock, it will be horizontal wells. And in horizontal wells, there will be big fractures. And these fluids will be going out through these fractures, not through these wells, basically, to the rock formation. All right, so it has 3 cycles, 3 steps in each cycle. You inject the gas, okay, in this example, it's carbon dioxide. So carbon dioxide goes in and it can mix with the oil. And when it mixes with the oil, it swells the oil, its viscosity goes down. At this point, you actually shut in, okay? That's, you shut in this well, so it's called the soak time, and it's of the order of weeks, and let the diffusion and mixing take place. And then you try to produce back. When you produce back, the dissolved CO2 comes out of the oil, but in the flow, there is a hysteresis. Now, in order for this gas to expand within the pore, some oil gets pushed out, and that's the oil that comes into the wellbore, and you produce that. All right. So this is a huff-n-puff process, and important points in these are the pressure, the maximum pressure you go to, because that pressure will determine how much gas can dissolve in the oil, and the minimum pressure you come to, that's the puff pressure, and that tells you how much gas comes out of the oil. Okay, so huff pressure and puff pressure and the soak time, these are some of the important numbers that you got to pay attention to and design that properly. All right, so in US, people are trying this out. CO2, you can use CO2, or could you replace CO2 by hydrocarbon gas? That's the question we are asking here. So CO2 you can use, because CO2 is very miscible with the oil at pressures above its critical pressure, which is like 1070 psi, which is like 70 it's about 7 megapascal or 70 atmospheres. And the reservoir pressures in these reservoirs are much higher than that. They are more like 3,000 to 5,000 psi. which is roughly 20 to 40 megapascals. Okay, so CO2 is a good solvent, mixes with oil, works very well. But the downside of CO2 is not available everywhere. You need large quantities of CO2 to do this. And if you don't have it, then you can't do it. That's as simple as that. The second thing is it is corrosive. So you have to have the well bores, which has to be made out of very good steel to avoid corrosion. Whereas if you use hydrocarbon gases, their miscibility with CO2 with oil is not as good as CO2, but they could be miscible depending on the composition of this hydrocarbon gas and the pressure. And definitely they are available in most wellbore sites, because wherever you produce oil, there is some associated gas. And out of that associated gas, you can get the enriching components such as ethane, methane, etc., ethane, propane, etc., and use more of that in this gas that you inject. So they are available. Okay. But the miscibility may happen at a higher pressure. Okay. All right. So in this particular project, we used something called this Mancos outcrop shale. And this shale has 27% clay, it has 47% quartz, and has also 20% carbonate. Doesn't have much organic, just a little bit of organic because it's an outcrop. The real reservoir shales would have a lot more organic part of it. So because it doesn't have much organics, but the reason we use these outcrops, because they're available from a company, we can order it and get it easily rather than real reservoir shales, which you have to get it from an oil company. So we put in some oil into it to represent our oil. And this oil we put in is a very light oil, or basically kerosene. Okay, it's a very light oil. We inject that into this outcrop rock to represent our shale, organic shale. And in this particular experiment, we worked with a gas, hydrocarbon gas, which is 60% methane and about 35% ethane and 5% propane. This is an enriched gas. The typical gas that you produce with oil is more like 90% methane and the rest is ethane, propane. So this is an enriched gas composition. So we need to do these studies with different gas composition to see how they work. So this is just one example. So this is how we first set up the core. The saturating the core, these rocks with oil is not a simple thing. In a conventional reservoir rock, it's very simple. You can clean the whole core out. You can inject whatever brine and oil into it very easily within a day or two. Here, if we try to do that, it will take, because the permeability is so low, it will take, a long time. And the other thing also, these formations have a lot of clays. You cannot totally dry them out. If you dry them out, you break their structures, native structures. Okay, so it's not the same thing. So we don't want to also totally clean it out or totally dry it out. So that's why just saturating it is a little bit of a challenge. The way we do it here is we vacuum the core for some time, first wait, then vacuum it, and then we we put inside a pressure vessel like this and inject the kerosene into it, fill these gaps with kerosene at about 2000 psi. And then we raise the temperature to sort of a typical of the shale reservoir temperature. In this case, we went to only 75 degrees C. Shale reservoirs go from 75 to about 130 degrees Celsius. When we raise the temperatures, the fluid expands and some of the pressure goes up. The pressure actually goes up to like 7,000 psi. and we just leave it at that condition for 2 weeks. So with that pressure gradient, some oil does go into this. So that's how we saturate these samples. Okay. And after we have those samples, this is the way we do our huff-n-puff experiment. So we take these things in some pressure cell and we inject CO2 into it. So CO2 fills up this gap. Then we increase that pressure to whatever huff pressure is. And in the experiments I'm going to show you, these are the 3 pressures we worked at. So we go to one of these 3 pressures. Okay. So at this high pressure, some CO2 will go into it, first due to pressure, then due to diffusion. Okay. So we leave it there for at least a day. So that's a soak time is a parameter again. So in this case, it was 24 hours. And then we decrease the pressure to 2000 PSI. That's our puff pressure. Then you can see some CO2 and the oil will come out. And we repeat this thing 3 times. There are 3 cycles like that. And at the end of the experiments, we do an NMR experiment. Okay, actually, we do this NMR experiment before and after all these things. And this NMR experiments helps us identify how much liquid is there inside these shales, and how much from that we get how much liquid comes out. So let's talk a little bit about this NMR. So this is a low field NMR that we do on our core samples. And this NMR is basically proton hydrogen NMR, and it finds out how much hydrogen you have. Okay, so here you see a time. This is the relaxation, spin relaxation time for these hydrogen atoms. And this is the time, and this is how much of that hydrogen exists. So this much at about 0.3 milliseconds, this much hydrogen relaxed basically. And if you take the cumulative of that, you get the total amount of hydrogen from which you can figure out how much liquid you have. Okay, so this cumulative graph gives us how much liquid we have. And these times tell us how fast are these atoms, or how fast does the water or oil is relaxing inside the pores. These spins relax faster when any molecule hits the surface of these pores. So it's indicative of a surface area, which you can convert to some kind of pore size. So basically, something which is relaxing at about 10 milliseconds is in a bigger pore than something that's relaxing at about 0.1 millisecond. So in some sense, you get a pore size distribution of the fluids you have in this differential incremental volume. Okay, so that's what we are getting. And just this T2 NMR does not distinguish between water and oil. For that, you have to do more complicated NMRs. And we haven't done that in these experiments.
I have a small query, Professor Mohanty.
Yes.
Is it why the nature is wavy here? I mean, typically at 1 millisecond, there is a minima, and then at 10 is the maxima.
Yeah, yeah. So this is basically showing there are 2 kinds of fluids maybe here. Okay, so water will relax in a little different way than oil. Okay, so it could be that, or there could be a dual pore size. Okay, sometimes the pore sizes are not, that is not just one pore size. If you have one pore size, you'll get one peak. If you have dual porosity in these shales, we have a lot of different types of pores. So that's why also you get several peaks over here. Okay, so it relates to pore sizes. And actually, it's a little more complicated. It's pore sizes, wettability, and a little bit of what's the mineralogy on the surface of the pores, that also tells you how fast things are going to relax. Okay. So yeah, so just from this graph, we can't get totally about the pore sizes or the wettability, but it gives you some impression of that. And there are some more complicated algorithms you can do, the T2, D2 and all that. Then you can distinguish between oil and water. But in these shales, the volumes are so low, the errors in these calculations are also quite large. In a conventional rock, it's much more useful. All right, these are the experiments we did in the first set. So let's look at that a little bit. We have a control experiment where we just raised, we put a sample there inside our pressure cell, just raised the temperature to 75 degrees Celsius and brought it back to room temperature. And then we took and did the NMR and see what difference do you get. Okay. So that's just to see just temperature variation, what's it doing. In the actual experiments, like CO2 experiments, here we went to a pressure of 2800 PSI. We soaked there for a day, and then we brought it down to 2000 PSI, so huff-n-puff, and we did 3 cycles of it. Similarly, this one is at 4000 PSI and CO2. This is at 5200 PSI and CO2. And we did the same thing with this hydrocarbon gas at 3 different pressures. So let's look at some of these results. So in the control case where we just raise the temperature, no, sorry, this is not that. This is just showing how much oil we are putting in. Okay. So this is our initial, the blue curve here is before we did anything, just the core as it is, and we have vacuumed it for some time. And when we take it out and do the NMR, we see this, which shows that even in this core, there is some amount of liquid. Okay, the blue curve shows there is some amount of liquid. Okay, so that's what it's showing. Then after we did, we pressurized with oil and tried to inject some oil into it. This is the graph we get. So now you see there is a peak coming in at about 10 milliseconds. So that's basically the oil that we injected into it. Okay. So this is definitely the oil we injected. This is whatever is there in this core before we did anything. Okay. So I would guess this is mostly water. There may be a little bit of organic oil there too, and there are some adsorbed organics also related to this. All right, so this is the amount of oil we are putting in. And if you take that, you can figure out how much oil you injected. So if you look at this, the first 4 samples we had done at one time, it's of the order of 0.5, 0.6 milliliters. That's how much we are putting in. And this is another set we did like a year later. So at that time, maybe the samples are a little different. So we put in a little more over there, about 1.2 ml. We also did this calculation by just weighing the samples, and they confirm about what we saw in the NMR. All right, now the control experiments. In this experiment, we are going to just raise the temperature and bring it back. There is no pressurization or anything like that with any gases. So as you can see, both the things are about the same. So just raising the temperature doesn't do a whole lot of taking these fluids out. More or less the same. Here is the typical experiment from the CO2 huff-n-puff. So the blue is again the initial. This is the oil saturated one. And this is after 3 cycles of CO2 huff-n-puff at 2800 PSI. Okay. So what you can see here, that by doing this CO2 huff-n-puff, we have definitely removed most of this peak. So most of the oil we had injected, we have removed that. We have also removed a little bit of fluids that was originally there. Okay. So this is a little bit lower than that. Right, and this is with the hydrocarbon gas. So very similar sort of behavior. As you can see, with this hydrocarbon gas that we are using, which is like 35% ethane and 5% propane, is quite effective at taking out the oil. And here is what we get in each cycle. Each cycle data doesn't come from NMR. This comes from just the mass balance, whatever is coming out. And of course, it's not very accurate, but still gives us an indication that in the first cycle, we get about 75% of the oil that we get out on total. And this is, so with subsequent cycles, the amount of oil you produce goes down. Okay. Here is what you get with CO2. You can see this is the original liquid there, and this is the amount of oil we put in, and this is the amount of liquid that we take out. Okay. This is roughly 40% of what the fluid that's there. Okay. So this huff-n-puff process with CO2 takes out roughly 40% of the liquid that we have. And changing the pressure didn't change very much as long as you are above this pressure. Okay. So this pressure actually is above the miscibility pressure, minimum miscibility pressure for this oil, which is roughly about 2300 PSI. So if you are above that pressure, the pressure almost doesn't matter. You get about the same amount of liquid out. This is with the hydrocarbon gases. It's very similar, as you can see. All right, so this is just putting together the last two set of slides, basically, showing that we get about 40% of the liquid out, and it's independent of pressure, and really not much difference between this hydrocarbon gas and CO2. So you could replace the CO2 with hydrocarbon gas. In fact, in West Texas, where they're trying to do these things, there is so much gas production, there's a glut of gas. So the value of ethane is practically zero right now in the West Texas area. So they are thinking, a lot of the companies are thinking of just doing this hydrocarbon gas huff-n-puff in that region, because these solvents are almost free to use. All right, so simple conclusions from here. We can replace the CO2 with hydrocarbon gases. Okay, and they show good potential, about 40% of the oil in this little core. Of course, you have to do the calculation and figure out how far your diffusion fronts are propagating, and what kind of time does it correspond to in the real field situation. All right, here is a variation on that. Can we improve this gas huff-n-puff by doing something with the water? Okay, so we still want to use the gas for the same reasons, but can we add something to improve the recovery? So in the water, we can add something that can change wettability. Okay, and if you can change wettability from oil wet to water wet type of direction, then you can spontaneously imbibe some water. If you spontaneously imbibe some water, water goes in, it has to push out something, and that would be oil. You can also reduce interfacial tension, so the flow is a little better at this fracture matrix interface. All right, so we do the same kind of experiments. Depending on which experiment we're doing, we inject this chemical blend, which is basically a surfactant water. Sometimes we have some other additives also to change wettability. And then you pressurize with the CO2, and you repeat cycles. Okay? And you do NMR before and after. In these experiments, when we inject any water-based chemicals, instead of using water, we used deuterated water, D2O, instead of H2O. D2O doesn't have any signal in that NMR, T2 NMR spectra that I was showing. So any water that goes in won't show up, almost, okay? So then you can see how much the original fluids you have removed. So that's the only difference over here. So here are 5 experiments for comparison. The first one is the control, just like before, it's the same one actually, probably. This is the CO2, again, similar to earlier. And this is this chemical blend plus CO2, okay? And the other one is, this is just brine, instead of, so brine with no chemicals and CO2. So we wanted to make sure that chemicals are actually doing something, not just the water part of it. Okay, so it's brine plus CO2. And this one, we changed the order in which we inject. So we first injected the CO2, then we injected the chemical blend. This is something actually a lot of people in the field would like to do, because to inject CO2 at high pressure, you need big compressors. And there are actually a lot of shortages of compressors now in West Texas area because everybody is trying to do this. So what you can do, you can inject CO2 up to a certain pressure, intermediate pressure, by a gas compression. Then you can inject these water-based chemicals directly, and you do that with a pump, and it's much easier to inject at a higher pressure because they are more or less incompressible. So when you inject that, that goes and pushes the CO2 in and compresses it. So you can cut some of your costs that way. So, but the order of this could make a difference. That's why we're doing this experiment. And this one just shows the oil saturation step. So basically, again, about 0.5 to 0.6 milliliters of oil was injected by the procedure we talked about earlier. So then we do these experiments. So again, let's go through this. The first one is the control, is the same one, basically doesn't do much, recovery factor 1% or negligible. Okay. So then CO2, like we saw in the last case, it's of the order of 40%. Okay. Now we do this with the chemical blend and then CO2. So having the chemical blend improved the oil recoveries significantly to about 60%. Okay. And then we did an experiment with just brine, and that did not increase it that high. Okay, so chemicals are doing something there. Okay, so we want to understand that. So we designed these chemicals by doing a lot of wettability experiments and inhibition experiments. That's how these chemicals were chosen. All right. So if we look at the NMR imprint of these processes, let's go through that. For just CO2 we had gone through, we saw that this injected oil almost goes away, right? And we saw we get a little bit of oil, liquid out. So because the red was sort of the oil saturated state, this is after the CO2 huff-n-puff experiment. That goes down a little bit, we get some of the liquid out there also. With the this chemical blend, we remove a lot of, so this is oil saturated, and this is at the end of the experiments. This signal goes down significantly in addition to this signal going down. So a lot of the water, the liquid that was there was removed by this injection of this chemical blend. Okay. So that's why we got additional 20% oil recovery in this case. If you just do brine, you do not remove a lot of that signal. This signal moves to little bigger pores or something. So, but you don't remove this signal totally. Okay. So as I was saying, gas compression is an issue. So we are, if you are going to do gas, this chemical injection and then gas injection, you have to go to this high pressure of the order of 4,000 PSI with the compressor. Instead of that, we could do the other way, inject the gas up to some pressure like 2,000 PSI, then use the chemical blend to go to that higher pressure. Okay, so that's the experiment we did, which is the last experiment over here. And in that case also, we got about 60% oil recovery. Shows that by changing that order, we can still get pretty high recovery, and we can, this may be a favorable way to inject in the fields. In this case, also you can see the NMR. So this is the green one is the new one that showed that was very similar to the other one. So you can see this. They removed the liquid signal from here quite a bit, and that's how the oil got out. So concluding this part, for the shale oil EOR, CO2 huff-n-puff combined with these chemical blends can improve the oil recovery from about 40 to 60%. Chemicals in the chemical blend can oil recovery by wettability change, lower IFT. And sometimes we add in a little chemical to increase the permeability in the fracture matrix interface also. So NMR spectroscopy is a good way to find identify these mechanisms. Pressurizing the injected gas by injecting chemical blend or water can lower some compression force in the field. All right, how am I doing on the time? I have one more topic over here. We can go over, or we can skip that.
No, we can go over, no problem.
Okay, all right. So this is a slightly different topic. It's about micro-encapsulated acid. As we know, when we create a fracture, a lot of proppants settle down near wellbore, and they definitely don't go very far and don't reach the microfractures. So a lot of the microfractures are closed in, after this hydraulic fracturing process. They open up, but then they go back and close in because there are no proppants to keep it open. So what can we do? So our idea was, how about we do a little bit of acid treatment? We put a little bit of acid to etch these microfractures so that they open up. The problem with just injecting bare acid is that if you put acid, it will go everywhere. It will react with the surfaces everywhere. So a lot of acids will be just consumed in the wellbore, in the main hydraulic fracture, and not much will reach to the microfractures. And that also, when the acid, if you put acid everywhere, they eat up a lot of these carbonates, and the whole shale becomes softened, and then the fractures close. Okay, fracture conductivity actually goes down. So instead of injecting bare acid, we thought, can we encapsulate the acid and inject it? Okay. So that's the idea of this micro-encapsulated acids. So we want to encapsulate the acids in these little spheres, and these spheres will have a density similar to water. So when you inject with water, they will not settle down with gravity. They'll just go with the water and go wherever water goes. So they'll get into all these microfractures. And when you, at the end of hydraulic fracturing, when the pressure goes down, so everything collapses. So these fracture surfaces will collapse on each other. So these things will get pressed, they will break, they will release the acid. Okay. So how do we encapsulate these and create these micro encapsulations? So here you can see we have, this is the acid, and we have just colored it blue so that you can sort of see it. And it has 15% hydrochloric acid. And these are some hydrophobic nanoparticles. Okay. So we take them and mix them. Okay. When we mix them, it makes these drops or encapsulated acids. So you get a coating of these nanoparticles around the acid or the water phase. You can do this with acid or any water phase, you'll do that. So it makes these particles, okay? as you can sort of see, these are particles. So you can see it's piling up. It's like sand, looks like sand almost. Okay, but so you make these particles by doing this, and you can sort of you can look under the microscope and see how big these particles are. They're about 27 or about 30 microns. Okay? And inside them, you have the acids. That's why after they have been encapsulated, you couldn't see that color. Okay? It looked white. So if you take these acids, okay, and you keep it in a container or in an, you make a emulsion out of it, you leave it for hundreds of hours, they pretty much stay there. There's very little acid that comes out of there. So the relative powder height remains almost the same. But if you make a traditional acid in oil emulsion, okay, this is the alternate technology, you can encapsulate that way also, then the stability, thermal stability is not very good. Okay, so in an hour or so, these emulsions rupture and acid is released. But here you can keep it for a long time, and even at high temperature like 80 degrees Celsius. So if you, we took some shale fragments and dipped it in different acid forms, okay, and to see how much of that is reacting, okay, or how much acid is basically outside. Okay. So if you take, so we have a comparison of 4 things over here. This is for 1 weight% acid concentration. This is for 10 weight% acid concentration. So this red one is basically just bare acid, non-encapsulated acid. Okay. The blue one is acid in oil emulsion. That's the traditional technology. Okay. This green one is basically bare acid. It's basically if you take our encapsulated particle and crush them, then it's that one. And this one is our acid in air particles, okay, uncrossed. So basically, if you take these shell particles and mix them with these particles, they don't react very much. But if you did that with an acid in oil emulsion, they will react quite a bit, as shown here, just like just open acids. Okay. So by encapsulating them, you can protect the main fracture surfaces, all the tubular surfaces from this acid. Then we try to see how much conductivity we can increase by using these particles. So for that, we took some shale cores and cut it, and we created a fracture over here. Then within this fracture, we put in a layer of these encapsulated acids, particles. And then we put it inside a core holder, and then we flowed fluid through it. And then we applied the overburden pressure, crushed these particles, and let it react with the acid and see how much the conductivity of this fracture changes. Okay. So here are these experiments where we have plotted here the conductivity of the fractures before and after. Okay, this is before, this is after. This is with different concentrations of acid. So let's just look at this 10 weight% acid. So in here, as you can see, the fracture conductivity was of the order of 0.3 millidarcy feet in this case. But after the treatment with our particles, the conductivity went up to 1.2 millidarcy feet. With 15 weight%, and this blue thing shows the amount of increase. So it went up roughly three, four times over here. Okay, with 15 weight% acid particles, it went up almost 40 times. Okay, so we can increase the conductivity of these microfractures significantly if we can use these particles properly. Here is why that happens. This shows some ACM pictures. So what we see that, we have before treatment with these particles, the surface was pretty flat. And then after we treated with these things, it made a lot of pits over here. Okay, so basically, wherever these particles were there, and they got crushed, some acid came out, it reacted, made the little pit over there. So we created a lot of pits. So if you can create a lot of pits like that, then you can develop some conductivity. So that's how we are increasing the conductivity. All right, so let's conclude this part. This micro encapsulation of acids can be used to can be made by using hydrophobic silica nanoparticles, which are fairly cheap. And these MEA show excellent thermal stability. To release it, we are using the pressure from mechanical crushing when the fracture closes. And these unpropped fracture conductivity of Eagle Ford shale can be increased significantly by doing treatments of these things. So we think we can inject this sort of particles ahead of the real fracturing in the front part of the fracturing fluids. So they will go into these microfractures and then create and have some microfracture conductivity that will stay for a longer time and thus give higher productivity. So with that, I want to thank all the companies that support our consortium. And I'd like to thank you for listening to this talk. And I'm open to take any questions you may have.
Thank you, Professor Mohanty, for a very nice talk. So we are now ready to take any questions from the audience. So there's already one in the Q&A panel, which is asking you to discuss the environmental implications of the methods that are being used. And a follow-up to that, which is asking about whether you can say use something like shock waves, so dynamic stimulation, explosive stimulation.
All right. Okay. So the first thing is what are the environmental implications? So since I talked about sort of two things, one was CO2, the other one was this acid. So the CO2, if we can use CO2 in doing this huff-n-puff process, and then at the end of these processes, we are basically exchanging the hydrocarbons for the CO2. So we can store some amount of CO2 in these reservoirs. So that could be a plus, all right? In terms of the acids, the amount of acid we are going to use is very small. And these acids are going to go and react with the calcium carbonate, magnesium carbonate minerals that we have there. So the acid will react and your pH is going to go to neutral at the end of it. So there are no issues of this acids breaking through and coming to the surface or anything like that. So, and these formations are at about 3,000 meters deep or more. So I don't think this will have any impact on the environment of subsurface. Okay, so that was the second part. And then the other question was using shock waves. So I'm not very good at the mechanical aspects of these fracturing things. So I don't know a good answer, but I think people have tried different kinds of fracturing techniques, and a lot of them haven't worked out. And these are some of the things that worked out is what they're practicing. In fact, they even tried having a little nuclear blast underground in the 70s in US to create a lot of fractures. And that didn't happen. That didn't create the right kind of fractures because of very high temperature, and it sort of became more like a glass rather than create fractures. All right, next question.
Yeah, the next question we have is by Shilpa Nandwani, and she's asking, can we use carbonated water instead of a chemical blend?
Okay, so the carbonated water, the capacity of water to solubilize CO2 is not a whole lot, okay, compared to injecting some amount of CO2. You can find the exact numbers. Only a small part of that CO2 that, let's say, we used in our experiments will dissolve in the water, a very small part, meaning like 1 or 2% of that CO2. So by carbonated water, you cannot put a whole lot of CO2. You can put some, but not a whole lot of CO2. And just the little bit of CO2 that you inject would be useful, but it cannot do all the things pure CO2 injection is doing.
Okay, so the next question is by Mayank Rakesh, and he's asking that dry ice is one of the most common and a very powerful explosive. Is there any way to use that for fracturing, or is it being studied right now?
That seems like a good idea, but I don't know if somebody is studying that. But I think people are looking into some kind of micro explosives. If you can put something and that expands in volume significantly upon a trigger, I think that could help. But I don't know if somebody is studying that right now. But I think it's a good idea. Pursue that.
So the next question is by Saket, and he's asking, did increasing the concentration of high pressure gas in a void, what effect does it have? Will it initiate shearing action as the latitudinal strength of shale rock is not very high?
Lot of the fracturing is actually done with the shearing action. When they do this hydraulic fracturing, is the shearing action that creates the fracture, rather than the more of the compressive or the normal stress type of thing. So again, I'm not an expert on the mechanical side of fracturing, so I think you have to ask that to someone else.
So the other question is from Chandan, and he's again asking, I guess, a mechanical question. He's asking if the energy released during the propagation of the fracture tip is greater or smaller than the energy applied to the original fracture.
I would guess, from just thermodynamic point of view, it will be less because some of it will be lost in the rest of the fracture. But yes, a lot of the energy is concentrated at the tip, and exactly what is happening at the tip is important. And the exact stresses you have, and the chemical nature, and the breaking of the bonds, that's all. Those are all important issues.
And he's also asking a follow-up, and he's asking if there is any way to determine the flow regime of the fluid that is flowing through a fracture.
So the flow regime?
Yeah.
Okay, so you could, I guess you could come up with the rate at which the fluid is flowing it's definitely near the fracture. It's probably, the dimensions are small. The fluid at that point won't have much velocity. I think the fluid regime will be laminar, right at the tips. Yeah.
I have one question, Professor Mohanty. I think, Chandra, I think we have over questions from the audience, right?
Yes, you can go ahead.
Just one small question. The outcrop that you have mentioned, are they preserved one, or because I see that 0.1, 0.2 milliseconds, there is a peak that you have shown, right, in the original outcrop. So are these preserved one? Because if I keep it at surface, maybe the fluid may dry up over a period of time.
Right. No, so these things they're not preserved in that sense. I think they have, there is some water that will evaporate away from these things. So I don't think it's preserved. It's sort of naturally what you get, and they're just stored in open. They are not stored
in case. I mean, if we order this outcrop from US, and then so we'll get the similar condition that what you have presented, right?
That Kyocera or something like that. There is a company in Texas which sells a lot of these outcrops for conventional as well as unconventional geological species. Yeah, that's where.
And then you talked about the wettability, the chemical blend that you have used, right? You said that it could alter the wettability. So have you seen any kind of wettability alteration, by the way, in the original shale samples?
Yeah. Because actually, we have in actual Eagle Ford shale samples. We have a paper in 2019. You may want to look up. It's a SP paper, and there we took real reservoir Eagle Ford shale samples and saw that that looked like oil wet or more oil wet than water wet, and they are all mixed wet to some extent, okay, but they are more oil wet than water wet. And by treating with some surfactants, you could change the wettability, apparent wettability, towards more water wet. Yes.
And do we need to optimize the composition of the hydrocarbon gas? Because I think the one that you have used is the constant composition. But correct. Is there any studies impact on the recovery potential of the oil?
Right. No, that's a very good question. In fact, that's what we are doing right now. We are trying to change the composition and see what effect it would have.
Oh, that's great. The last question, the micro encapsulated acid that you have talked about, right? So that's I think the nanoparticle, right? Possibly silica nanoparticle that you have used.
These are just silica nanoparticles.
Silica nanoparticle, right?
But so they have been modified wettability. They're all.
So the acid goes in their pores, or I mean it like forms a suspension of this nanoparticle in acid, or
so I think the acid doesn't go through these particles. The particles are just coating it. These are spheres of roughly spheres of water which have been coated with these particles. Okay, and since they are hydrophobic, you can sort of encapsulate it.
So the acid sits on the surface of the nanoparticle, right?
No, so acid is in the bulk water that's inside these.
I guess because you have shown the dried silica nanoparticle, the video. So these are not encapsulated nanoparticle, right?
No. These are just simple nanoparticles with some silane coating, something that makes it hydrophobic.
Okay. So you make an emulsion, like acid in water emulsion with nanoparticles, right?
Yeah. It's almost like that. Yeah.
Oh, I see. Great. I'm done. Chandra.
Yeah. So I think there's a couple of other questions from the audience again. So one question is asking you if you have used any other chemical encapsulation except acid, like surfactants.
Yes. Yeah. Actually, we have done with different polymers. So there are different applications of this. You can apply to a lot of different areas. We have done some polymer encapsulation. the surfactant is a little tricky. If you use a lot of surfactant, this won't happen, because the surfactant will go absorb and change the wettability, and things change. But you can encapsulate polymers, and you can encapsulate other chemicals.
Okay. So then there is also a follow-up to that question, and they're saying, if I get this right, this micro encapsulation works as a proppant, and can their size be controlled, or does the size even matter?
Yeah, sorry. Actually, I probably didn't explain. These micro encapsulated particles are not proppants. What we are doing is we are putting them as particles, but then when the fractures close, they're breaking and releasing that acid. And that acid reacts with the carbonates in the shale and reacts chemically and makes holes there, basically. And that's what creates channels on the surface of that fracture, which gives it some permeability. Okay, so in this case, we're just putting acid there. It's just that we are just, the release of acid is delayed by this sort of mechanism. It's possible that you can encapsulate something else, like you can encapsulate a particle also inside this, and then they will act like proppants. Okay, so that's possible, but that's not what we did.
Okay, so I think we have exhausted all the questions in the panel.
Chandra, I have a quick question.
Yeah.
Yeah. Thanks, Professor Mohanty. I think it was a really nice talk. I'm just curious about this microencapsulated acids. Like, so when you're injecting at a particular pressure, do you think these microencapsulated acids will be stable enough and then reach the particular fracture and then stay there until you apply even more pressure? I'm just concerned that this will disintegrate even before that. Or
Right.
I'm curious if you have.
Yeah. So I think just a liquid pressure around it doesn't break it. Okay. But some kind of asymmetric pressure, that's coming from like the two sides of the fracture closing. That's what crushes it. Okay. And there are also other ways of releasing that thing or breaking these particles also. By using different chemicals, you could also break these particles. But just the liquid pressure around it will not break it, because they will be same in all directions, right? So that won't break. Yeah.
Thank you.
Do we have any further questions from the audience? Okay, if not, then I would like to thank Professor Mohanty once again for a very nice talk, and for accepting our invitation to speak at the webinar series. And as we mentioned at the beginning of the talk, if the opportunity comes, we would be very happy to host you at IIT Madras physically, as a next step from hosting you virtually.
Yes, sounds very good. We definitely look forward to seeing you maybe sometime next year.
Yeah.
Thank you very much.
Thank you, Professor Mohanty.
Yeah.
Thank you, Professor Mohanty, again for accepting and being here with us virtually.
Thank you, Jitendra. It was my pleasure.
Yes.
All right.
Thanks.
Good night, everybody. Yeah.
Bye.
Good night. Have a nice day.